Hi, welcome to this presentation on return-oriented programming, better known as ROP. Before getting into ROP, we need to understand how it came about. Memory corruption exploits, such as buffer overflows, have long been used by exploit devs. Execution space protections were developed directly to counter this. This mechanism marks certain areas of memory as non-executable. So let's say, for example, an attacker is able to overwrite EIP with a buffer overflow attack and get shellcode onto the stack. This shellcode won't be able to execute because that area of memory will be marked as non-executable. On Windows, this technique is known as data execution prevention, or DEP, and ROP was developed specifically to defeat this mechanism. So, how does it work? This technique gets its name from the fact that it uses sequences of instructions that all end with a return. These sequences are already present in memory, so we know that they're going to be in executable space and won't trigger an error through DEP. These sequences are known as gadgets, and they're the basic building blocks of a ROP exploit. By ending with a return, these gadgets can run an instruction and then return back to where the next gadget will be stored, allowing them to be chained. This is appropriately called a ROP chain. By chaining these instructions together, exploit devs are able to create behaviors that can be used for malicious purposes and be utilized in an exploit. So, the easiest way to form an exploit is to utilize built-in system calls that will disable DEP. A few of these are virtual alloc, virtual protect, heap alloc, and set process DEP policy. So for this demo, we're going to be using virtual protect, but it's important to understand how each of these functions work, as well as each of the parameters that go into them. So I've provided links to the documentation for some of these functions. I definitely recommend doing a deep dive into each of these before moving on and trying to form your own ROP chains. So, to build a ROP exploit, first we're going to need a pointer to the system call that we're going to be making, as well as each of the parameters, and we're going to need them to get onto the stack. Again, this is why understanding those functions are so important. We're also going to need a way to jump to the shellcode. One way to do this is through jump ESP, but other exploits might copy their payload into a different region of memory, so you're going to have to be creative with how you utilize your gadgets. Finally, a push AD instruction is used to get all the registers onto the stack so that we can prepare it for being run. So building a ROP chain is a fairly advanced technique, and it can often be a pretty tedious task. So thankfully, we have tools that can help automate much of this process. Mona is a tool that is used in conjunction with disassemblers, and we can use them to automatically find useful ROP gadgets in memory, and they can even go as far as to build ROP chains themselves. So, onto the demo. This demo will be using a Windows 10 system along with the immunity bugger. And we're also going to need to have Python installed because Mona runs on Python. So the first thing we're going to have to do is to ensure that DEP is enabled onto the system. How we're going to do that is first we go to Control Panel, and we go to System, then Advanced System Settings, and then under Performance we hit Settings, And then we can go to the Data Execution Prevention tab. Now, we want to make sure that we turn on DEP for all programs and services except for those I select. And we want to make sure that the vulnerable application that we're going to be testing, server.exe, is not under the exception list. As you can see here, it's not, and DEP is turned on, so we're all good to go. So we can close out of this. So we are going to be opening up our vulnerable application in the Immunity Debugger. Open it up with its parameter, the IP, and a port. All right, now it's paused. We have it running. And we can run our first exploit. So this exploit is a simple buffer overflow, and it has some shellcode that will open up calc.exe. So we get it running, and we get an access violation. This is because it put its shellcode for calc.exe onto the stack, and when it tried to run, it got stopped by DEP. So we can confirm that DEP is working on the system. Now, we can go ahead and try building our ROP chain. So in order to do that, first we're going to have to install Mona onto the system. So we go to this URL right here, this GitHub repository, and we're going to want to get to the mona.py file and download it. After it's downloaded, we go to the Immunity Debugger directory, and we go to the PyCommands directory, and we just place it in there. I've already done that, so I'm not going to do it now. But after that, Mona is installed. It's as simple as that. So, just to make sure that it's installed, we can run the !Mona command. And as you can see, we get a man page for Mona with all the potential commands we can use, and we can confirm that it has been installed. So, a quick tutorial on some of the basic commands of Mona. We're just going to get this application running again. So, some things you can do to help build a ROP exploit. One of the useful commands is the find wild command. So find wild, and then the M flag with ntdll. This will be a module that will be searched for. And then the S flag is the search string. So we can search for potential gadgets in the modules that we select. So we can look for pop ex hashtag return. And go to log data. As you can see, we have 7 potential pointers that we found, and we could just take that address and copy them into our ROP chain. Another really useful command we can use is the ROP command. So ROP, and then just like before, we can choose our module. This time what we can do is *.dll. This will look through all of our libraries when searching with this command. And I'm not going to run this command right now because it takes a couple minutes to run. But the good thing about Mona is that it will output the results of these commands to text files. And we can find them here, again, in the Mona directory. So we have a couple. This is the output of the find wild command. And we have a couple here. One useful one that was outputted by the ROP command is rop.txt. This file will contain all kinds of potentially useful ROP gadgets, and we could look for any that we want with Control F. So one we could find is increment exe return. So we could just look for it and find a useful one. So right here we have increment exe return in kernelbase.dll, and we have the address right here. We could just copy and paste that. Another really useful file is ropchains.txt. This will look through the different libraries that were specified and build ROP chains for you. So we have ROP chains for different system calls that we discussed earlier. So we have virtual protect, we have virtual alloc, and a couple others. And we have the ROP chains built in all kinds of different languages. So we have one for Python right here, and our exploit is written in Python. So we could just take this and copy and paste it into our exploit so that it will go right before our shellcode. So I already have that set up in my second exploit right here. See, we have this copied over and we have it running right before our shellcode. So we have the server up and running again. So we can run this command, exploit.py, and we get another access violation. So why did this happen? We can do a little bit of digging, but if we look into the registers right here, we see all the different things we put onto the stack into our registers. And if we look at a couple of them, they don't match up with what we put on. Namely, we're going to look at it in a bit, but we have two registers, EBX and EDX. They were supposed to be hex 40 and hex 201. So something went wrong there. So we're going to go back into the ROP chain that we built. And as you can see here, we have some null bytes in 201 and 40, and this is likely the cause of why this exploit failed. We can also, before moving into the final exploit, we can go into that virtual protect function documentation and look into how it's set up. So it has a couple parameters here. And so how virtual protect works is that we need to put in a return address for where it goes back. We discussed it a little earlier, but that's going to be jump ESP so that we can jump straight into the shellcode. We need a size of how big of an area we want to free up to be executable. So that is the 201 that we saw earlier. And then we need a memory bit that's going to determine what the address of, or what the level of protections this area of memory that we're marking is going to be. So we put in 40 here, which will mark that area of memory as read, write, and executable. And then finally, we have one more parameter, and that is going to be another area of memory that gets the old values of the protections. So in our ROP chain, that just place in memory that is writable. So if we look at that again, we have right here. So first, this first variable is the pointer to virtual protect. So we put that into EAX, and then we just pop that into EAX, and then we move it into ESI. So ESI is our pointer to the system call, virtual protect. And then what we have is we have the call to ESP. We're going to put that into EBP. And then the 201 and 40, we're going to put that into EBX and EDX respectively. And then that pointer to the writable address, we're going to put into ECX. And then in EDI, we have an address to return. And this is because the EDI parameter, or EDI register, won't be used. And we don't want to put just anything in there because that could mess up our exploit. So we put in a return. This is known in ROP exploits as a ROP-NOP because this is the equivalent of a NOP. So a no operation, as you would see in assembly code, because it will just return back to itself and go to the next instruction. And then we pop into EAX a couple of NOPs so we can help slide into our shellcode. And then finally that push AD return. So how do we get around these null bytes in hex 201 and hex 40? So an issue you see a lot when building your ROP chains is that sometimes the gadget you're looking for won't be in memory, or other times you'll run into problems like this. Building ROP chains is very tedious and rarely works on the first try. There's a lot of troubleshooting involved. So what we have here are two ways we can get to the values we need indirectly. So what we have are these two values, FFFFF, DFF, and FFFFF, C0. These are the 2's complements of the values that we are trying to get. And as you can see, there are no more null bytes in these values. When we use the neg command with these values, we reverse that and indirectly get to the values you want. And then when you're working with ROP chains, you're working with a limited number of registers. So we can, you often have to come up with creative ways to kind of like work with that. So we are using the exchange command here to use EAX and then move it back into EBX. So if we take these two ROP chains and then we put them into our old exploit, we get the final exploit over here. As you can see, we replace those two sequences, and we can finally restart this vulnerable application and then run our final exploit. And as you can see, the shellcode has executed and we have calc.exe open and our exploit has succeeded. All right, so wrapping up, we want to talk about how we can mitigate ROP attacks. So one way we can do this is with address space layout randomization, or ASLR. ASLR helps to protect against ROPs by randomizing the addresses in memory, so it makes it difficult to directly refer to them, which in turn makes it difficult to hit the addresses of our ROP gadgets. The demo we just did had ASLR enabled, but if we were to restart the computer, the exploit would no longer work because the gadgets will all have different addresses. Other defenses for ROP are being researched, but they still lack the widespread adoption of mechanisms like DEP and ASLR, which come standard and are enabled by default on most major OSs. This makes ROP a serious threat in today's landscape and make it very relevant and an interesting subject matter to look into more. And that's all I have for you today. Thank you for taking time to watch this presentation. I hope you all learned something and hope you all have a good day.